Okay, let's go for chapter 9 for the design of permanent joint by welding center wire. So for the permanent joints by welding center wire, we typically gonna do like welding. We mean so we're gonna fix everything for the permanent. We're not disassembly anymore. For the like in the figure there, we mean we're gonna apply the welding, fix everything together. So therefore, we're gonna apply the welding as less as possible. Anyway, it means we just weld the workpiece together, and then we can apply the heat. So therefore, the heat generated at a point. So therefore, the heat gonna apply the stress into the workpiece anyway. So it's like it's gonna cause some kind of like a thermal stress to the point, things like that. It's gonna cause some kind of like a thermal stress in terms of elongations anyway. So therefore, it's gonna cause some kind of like elongation, and then so therefore the workpiece gonna do some misalignment all the way. So therefore, in these kind of things, we just not quite apply so many point of weldings anyway. So therefore, we're gonna apply as less as possible for the point of weldings. That's shown in the figure there. This is some kind of jig fixer. We're gonna apply some kind of like a flank, some kind of bearing, things like that. It's for the flanks of the bearing, whatever. Okay. So let's go for a type of weldings anyway. Typically, we're gonna have two types of weldings anyway. Gonna be 1.1. We're gonna have the fitted welds. Which means we're gonna have those work piece. We're gonna put down on two things together, and then we weld at the corner, things like that. And this one we're gonna apply the two work piece together, and we weld at the corners like that. And then we have to work piece together. These two figures the same. This is gonna be the side wheel, and we just weld at the side, and then this is gonna be the front wheel anyway. This is gonna be cylindrical type, things like that. Okay, you're gonna call it fitted welds. And then it's gonna be butt or groove weld, things like that. We're gonna have a work piece, okay, in line, and then we just weld the top and bottom, things like that. Sometimes we're gonna have V shape, and then we apply the welds at the top, things like that, in a V shape, things like that. We have symbol look like that, and then sometimes we're gonna have egg shape, things like that, top and bottom respectively, and a V shape with 45 degrees, whatever. And then for the butt welds, things like that, we're gonna have typically look like that. We're gonna apply the force of that, stuff like that, and then we have a third of edge, look like that, and then the area of the welds gonna be look like that. You guys may have quite familiar with kind of welding on the workshop practice on the second years, things like that. So you guys gonna have experiences, things like that. Okay, so therefore we're gonna have some kind of like a throat, things like that, and then the welds area is gonna be the A all the way, and the length of the weld is gonna be L all the way. So therefore the sigma is gonna be perpendicular to the force, things like that, and then F over H time L. H is gonna be the throat, and then L is going to be length, things like that. So it's going to be F over the areas all the way. So therefore, again, okay, if the we call the reinforcements can be desirable, the stress concentration at the point A, whatever. So you may figure out you're going to have a stress concentration because that's why the belt is going to be some kind of like a abrupt change of the area, whatever, things like that what I mentioned before. So that's why we have a weak groove, things like that. Okay. So therefore, these kind of things, see, you may figure out the force of F is parallel to the welt area, things like that. It's going to be F over the area. It's going to be the tau over the area, H time L, respectively. Okay. And then fillet welts again. Okay, this is going to be corner. Okay, welts look like that. And then the throat is going to be look like that, and then the leg is going to be edge all the way. So therefore, it's going to be 45 degrees. So therefore, the relationship to the throat and the legs is going to be T is equal to H time cosine of 45 degrees, which is going to be 0.70 time H respectively. This is the relationship of the throat and legs respectively for the fillet welds. Okay? And then therefore, in this kind of sense, anyway, in the figure 9.7, we have two welds area. The air force there is going to be parallel to the welds area, so therefore we have the areas is going to be two welds area on the top and bottom respectively. So therefore we're going to have 2 times T times L, things like that, because we have two areas right there. So therefore, we can figure out the shear stress. It's going to be F over 2 times T times L, things like that. And then we change the torque is going to be in the terms of length, things like that. Okay. So therefore, everything's going to be look like that sort of way. Okay. So therefore, going to be switch around between the torque and the lake. It can be do respectively. Another way around. See, you may figure out the F is going to be parallel again to the Wells area. Okay, F over 2 times T times L. Again, we change the throats to be the legs, things like that. It's going to be the same thing that what we have can be make calculation and the words on that again. And then you may figure out the force of 9.7 and 9.8 is going to be the tau is going to be F over A respectively. And then we can be able to mean the strengths of the weld joints anyway typically. Okay, then what I put a little read over here is that here the ultimate tensile strength sigma u and the u strength sigma y of the weld metal. The metals are typically based on the standards of the metal of the weld of the weld metal. If only the ultimate tensile strength sigma u is specified, the u sigma y can be estimated as of sigma y is equal to 0.82 times the sigma respectively. So therefore, we can estimate the tau sub y equal to 0.6 sigma y respectively. So therefore, the combined stress, if we just do the combined stress, we can make estimation to be tau sub y equal to 0.5 respectively. Example 9.1, you can make a calculation by yourself, have a look at it by yourself. It's going to be simple and straightforward anyway. Okay. And then 9.2 is going to show you some of the tau, okay, the shear stress due to the weld area, things like that, okay. And number 5 is going to be weld joint subject to the bending moments. Okay, you can figure out there we have two welds area. We're going to have F there. So if we move the F to be right there, okay. So therefore, this one is got to be the combination, okay, combination there. So therefore, okay, that's what I said in here. Okay, right there, we're going to have a direct shear, of course. Okay, I'm sorry. Uh, we're gonna have the direct shear there is tau is gonna be F over A, and then another one is going to the sigma is gonna be equal to sigma and moment times C over I. Okay, so therefore we're gonna have the combined stress, which is gonna be have a tau and sigma induced at the same time, and then we're gonna have a combined loading at the weld joints right there. So therefore we can apply the maximum shear stress failure theory. So therefore, this is the things that what we can do on that. And then we're gonna have right there, we're gonna have the I sub u can be able to just use a table 9.1 as the unit second moments of area, things like that for the I sub u for this kind of things. We're gonna have example, okay? So therefore, okay, let's jump this over. Okay, to have a quick look at the example on the example right there. Example 9.3. Okay, the what is said here: a cantilever cylindrical beam, as shown below, is subject to the vertical load of F. At the fixed end, the cylindrical beam is welded in a circular shape, as shown below. And given the cross-section diameters of the cylindrical beam, D is equal to 100 and A is 150, and then the weld measure have a sigma y of 462. You have the n sub y is equal to 2 to determine the legs of the weld. You may figure out it's exactly the same. We're gonna have a F right there. If we move the F up there, we're gonna have two stresses induced, going to be right there. F is going to be the shear stress, and then another one is going to be a sigma. Okay, we're going to combine loading. So therefore, I said it here is going to be time, tau, and the sigma respectively. So therefore, I have a tau sub y. Okay, look like that, and I sub u. Okay, going to be equal to pi to the power of third right there. Okay, and then I is going to be the t times I sub u based on the table 9.1 there, and then I got an I equal to tau the t times I sub u respectively. So therefore, I find the tau is going to be f over a respectively, and then I find the sigma respectively. Okay, I plug it back to the maximum success failure theory. Okay, and I just plug everything back in. So that's why I just got one unknown left over. I got the t there. I find the one unknown left over. T is going to be 2.81. I just switch it back to be the h, the legs there. I find h the answer is about to be 4 millimeter. That's the answer. Okay, this is pretty much straightforward then. And then 9.4 is going to be another example of the quite complicated of the bracket up there. We have one, two, and three web joints, things like that. Okay, kind of the bracket there. So we're gonna have the tau and the sigma respectively. Okay, we're gonna plug it in the maximum shear stress failure theory again, and then we're gonna have the answer look like that. Okay, and then another type is gonna be well just subject to the torsional loading, and again we're gonna have F right there, and then this one we're gonna have two welds on the top and bottom ladders respectively. So therefore you may figure out the F there. If we move right there, it's gonna be have tau 1 is gonna be direct shear there, and then the tau 2, okay, it's gonna be right there, okay, perpendicular, okay, to the R there. So therefore the tau 1 and tau 2 can add it up together. It's gonna be the total tau there, okay, by the vector polygon then. Okay, so therefore we're going to primary shear and secondary shear respectively. By the tau 1 is going to be F over A, and tau 2 is going to be torque times R over J, where J is T times J sub U, where the J sub U is going to be in terms of 9.2 respectively. We're going to have an example in the 9.5, things like that. Pretty much straightforward. Okay, you may have a look at it by yourself, things like that. And then we have a problem set. Okay, pretty much straightforward. Okay, number one, number two, number three, and then number five, things like that. Pretty much interesting. Of number seven, and then number seven is pretty interesting, things like that. Okay, you may have practice on it. Okay, it's gonna be it for the chapter 9. Okay, on the welding center way. Okay, I'm gonna stop on it on the chapter 9 then. Okay, that's just it. Okay.